Hi, we're here with the current balance again. Take a quick look at this. We've got the scale is set up with the magnets on it. There is no current flow. Power supply is off. Let's turn it on. We're up close to 2 amps. Mass is now 0.14 grams. Let's turn that off and see if that happens again. Back down to 0. Turn it on. So it looks like it's reproducible. Again, this deflection is occurring because of the Lorentz force. And if we switch the magnets around, what happens when we switch the magnets around? Okay, turn back on. Okay, so now we still have a change in mass, and the mass has changed. The change in the mass has changed sign. So instead of being plus 0.14 grams, it's now minus 0.14 grams. So something, this Lorentz force is somehow causing the magnet assembly to be lifted up a little bit. Okay, and some people had a little bit of trouble in the lab reports looking at the static equilibrium and how we related the Lorentz force to the changing mass reading that we got on the scale. So let's model our balance as a spring scale and see if that helps out. Let's see what that looks like. Okay, so let's suppose we have a calibrated spring, and the spring is calibrated, so we know that when we add a mass to it, we can tell from the displacement what the value of the mass is. So suppose with no mass added to it, it has an equilibrium displacement of 0. And now I add a mass to it, say our magnet assembly, it reaches a new static equilibrium at displacement x1. In this case, we have two forces at work. We have a restoring force, a spring force, and we have a gravitational force. Okay? So in static equilibrium, there are forces acting on this system, but the sum of the forces is 0. In this case, the spring force we know is kx1, and that is equal to mg. Okay? So now what happens? What do we do now? Well, what we're going to do is we're going to turn on another force. We're going to turn on our magnet force, and we're going to slightly lift up this mass. We're not going to completely overcome the force of gravity, but we'll reach a new equilibrium at a slightly higher position, x2. So let's see what that looks like. Well, now we've turned on our magnet force, so the mass has moved a little bit to a new position, x2. So we're in a new static equilibrium position. We now have three forces acting on this system. We have the spring force is still there. We have the magnet force, which is pulling the magnets up just a little bit. See, this is our Lorentz force, the interaction between the magnetic field and the current carrying wire. And we have the gravitational force again. So now in this case, we have Fs, our spring force. This is k times x2. We had it at a new position now, plus our magnetic force, our Fb. We're not sure what that is yet. We'll just call it Fb. Again, these are going to sum to be equal to mg. Okay, but we have another expression for mg. We know that mg for this magnet assembly is equal to k times x1. Okay, so rearranging this, this now means that the magnet force k, or magnet force F, is equal to the spring constant k times this difference x1 minus x2, which we can write as k times delta x. But we can rewrite k times delta x again. This is just delta mg for our scale. Okay, so this is how we can see that the magnet force should be equal to delta mg. All right, so I hope that makes things a little bit simpler for you, and good luck with the rest of your work this week.